In this video, we're going to look at graphing parabolas, which are the shapes of quadratic functions or equations. So we'll start off by looking at some of the introduction and theory behind graphing parabolas, and then we'll move on to look at 6 examples in total. 4 we'll do fully, and there'll be commentary on 2 more examples that you'll get to have a look at. So let's get started. So a parabola is the shape of a quadratic graph, and the most general form is y equals ax squared plus bx plus c. And if the a value, so that's the coefficient of x squared, if it is positive, then the parabola is concave up as shown on the screen at the moment. If, however, a is negative, the parabola is concave down, and that's the second graph that just appeared there. Key features of a parabola include the y-intercept, the x-intercept or intercepts if they exist, and we'll have a look at cases where they do and don't exist. There's also the turning point or the vertex of the parabola. And finally, there is a thing known as the axis of symmetry. However, we won't spend a lot of time on that in this video. So finding the key features, so the 3 to 4 things listed above, is a useful way to help graph parabolas. So when we think about how to graph a parabola, we need to think about finding those key features. So usually you'd start off by finding the y-intercept. It's one of the easier things to find. And to do that, you let x equals 0 and solve for y. Then you might move on to finding the x-intercepts, and for that you'd let y equals 0 and solve for x. And that often involves factorising and using the null factor law, or you might choose to use the general quadratic formula, or you could undo the completed square or turning point form of an equation. The discriminant can give useful information about the number of x-intercepts to expect. Then you could move on to finding the turning point. And there's a couple of ways you could do this. The first is that the turning point in turning point form, where you have y equals ax minus h squared plus k, the turning point is simply hk. Alternatively, the turning point exists on the axis of symmetry, which is given by x equals negative b over 2a. Another way, a little bit similar to the axis of symmetry, is to find halfway between the x-intercepts of a graph, and we'll have a look at that technique too in this video. Once you've got those 3 pieces of information, we simply plot the coordinates of the key features on a set of axes, making sure that you label all key features with their coordinates, and then we draw a parabola through the plotted points. And it's really important to make sure your parabola looks like a parabola, because the shape of these graphs is important. So it can't look too much like a V, so it can't have a really sharp turning point. It's got to have a smooth curve like the 2 we saw on the previous slide. One thing to note is that the method for graphing a quadratic will differ depending on the equation you start with. So depending on what it looks like to start with, you're going to find and solve for these different key features in different ways. So we're going to sketch the graph of each of the following parabolas, and we need to clearly label any axial intercepts and the turning point with their coordinates. And for part A, we have y equals x squared subtract 10x plus 16. So we're going to start off by finding the y-intercept of this graph, and we know the y-intercept occurs when x is equal to 0. Substituting that into the rule, we have y is equal to 0 squared minus 10 times 0 plus 16. So therefore, y is simply equal to 0, and then the second term is also 0, so we just get y equals 16. So then we can look at finding the x-intercepts of this graph, which happens when y equals 0. So in our equation, we will have 0 is equal to x squared minus 10x plus 16. And to find the x-intercepts of the graph, it involves solving a quadratic equation. And we know one method for solving a quadratic equation is to factorize and use the null factor law. So first we try and inspect, and we look for the factors of 16 that add up to negative 10. And in that case, we can identify negative 2 and negative 8 as being factors. So we can have 0 is equal to, and it's going to be x minus 2 times x minus 8. And again, if you were to check by expanding that using a grid, we'd get the original quadratic equation back. So that's the correct factorised form. So therefore, our next step says that x minus 2 could equal 0, or that x minus 8 could equal 0, so that's the null factor law. that says when two things are multiplied together, one or the other or both of them could equal 0. And then solving for x, we simply find that x could equal 2. So we add 2 to both sides of the first equation. Or we get that x could equal positive 8. And we would get that by adding 8 to both sides of our second equation. So the last thing we need to do is find the turning point. And for this example, we're going to do it by completing the square to get the quadratic into turning point form. So our parabola y equals x squared minus 10x plus 16. We can complete the square by looking at this b term here, or the coefficient of x. And what we want to do to that is we want to halve it. So we do minus 10 over 2 squared. So that's going to equal minus 5 all squared is positive 25. So to complete the square, we add 25 onto those first two terms. And so that our expression isn't changed, we simply subtract 25. And now the first three terms here become a perfect square. So therefore we find that y is equal to x minus 5 all squared. So that's the perfect square. And then left over is minus 25 plus 16, which is minus 9. So that means that the turning point will be at positive 5. So the 0 of the bracket. So we do x minus 5 equals 0, and we get x equals positive 5 out of there. And then the y value of the turning point is simply the negative 9. So that's minus 9 there, and that'll be the turning point. So now we know that the y-intercept is 16. We know we have x-intercepts at 2 and at 8. And we know that the turning point is at 5, negative 9. So we can use that information to sketch a full graph of this parabola. So there's two ways to do this. We could plot all of those points and join them up, or we could sketch approximately where we think the parabola is and then label the points second. For this video, I'm going to put the points where I roughly think they're going to be. So that's 0, 16. And then we have a point here that is at 2, 0 and at 8, 0. And then we have somewhere down here the turning point, which was at 5, negative 9. And now the job's just to sketch a nice parabola looking shape through all of those points. And that will be the graph of y equals x squared minus 10x plus 16. However, we're not quite finished yet. We've just got to label all those coordinates. So this is 0, 16, the y-intercept. This x-intercept was 2, 0. And the second one was at 8, 0. And finally, the turning point was at 5, negative 9. So that's the fully completed graph for part A. For part B, we're going to sketch y equals x squared plus 6x minus 7. I'm going to encourage you to pause the video and have a go at completing this before I go through the answer. So this question is very similar to the first. So we're going to go and find the y-intercept of this graph, which is when x equals 0. So therefore we find that y is equal to 0 squared plus 6 times 0 minus 7. So therefore y is simply equal to minus 7. And the next thing we can do is find the x-intercepts of the graph. So they occur when y equals 0 in our rule. So therefore we have 0 equals x squared plus 6x minus 7. And again, we're going to try and factorize this by inspection as being the first way of trying to find the x-intercepts. So here we can look for the factors of negative 7 that add up to positive 6. And we can use positive 7 and negative 1 to do that. So we're going to have x plus 7 and x subtract 1 in our factorized form. So a reminder that we were looking for the factors of negative 7 that added up to 6. So next we could use the null factor law, which says that x plus 7 could equal 0, or that x subtract 1 could equal 0. And for the first one, we could subtract 7 from both sides, and we'd find that x could equal minus 7. And for our second option, we could add 1 to both sides of that equation to get x by itself, and we'd find that x could equal positive 1. Next, we need to find the turning point of this parabola. And this time, I'm going to show you how to use the formula x is equal to minus b on 2a, or the axis of symmetry, to determine the turning point. So we know, or the formula says, that the turning point of any parabola is equal to, for its x value, minus b on 2a. So for this, it's going to be x is equal to minus b, which is minus 6 divided by 2a, which is 2 times 1. So therefore, x is equal to minus 6 on 2, which is simply equal to minus 3. So once we know what the x value is, we can find the y value by substituting that back into our original rule. So y is going to equal minus 3 squared plus 6 times minus 3 minus 7. So therefore y is going to equal minus 3 squared is 9, and then plus 6 times negative 3 is subtract 18, and then we still have minus 7. So therefore the y value is going to equal minus 16 overall. So the coordinate is going to be minus 3 comma negative 16. So once again, we've found all the key features. So we know the y-intercept is at negative 7. We know we have an x-intercept at negative 7 and another x-intercept at 1. And we have a turning point that is at negative 3 comma negative 16. So for this one, I'm just going to try and sketch the parabola approximately where I think it is, and then label the points. So the parabola is going to look something like this. And this is the point here that is going to be minus 7 comma 0. This point here is at positive 1, 0. So they were the two x-intercepts we found. The y-intercept just here was going to be at 0 comma negative 7. And finally, the turning point that we found was at minus 3 comma negative 16. So that's the fully completed graph for part B. For part C, we now have an equation in turning point form that we need to graph. So this time we have y equals negative x plus 4 all squared plus 5. So we're going to start off by finding the y-intercept of this graph. And again, we know that that occurs when x equals 0. So therefore, we find that y is equal to minus 0 plus 4 squared plus 5. So therefore, we find that y is equal to negative 16, because we have minus then times 4 squared. So negative 16 plus 5. So the y-intercept is going to be at negative 11. Then we're going to move on to finding the x-intercepts of the graph. So that occurs when y equals 0, and then we solve for x. So therefore, our equation becomes 0 equals negative x plus 4 squared plus 5. So we could subtract the term x plus 4 all squared from both sides, and we end up with x plus 4 all squared is equal to 5. And now we want to undo the square that's occurring to the x plus 4. So we take the square root of both sides, remembering that we get plus or minus the square root. So here we're going to have x plus 4 is equal to plus or minus the square root of 5. And then finally, to get x by itself, we're going to subtract 4 from both sides of the equation. So our x-intercepts are going to be x is equal to minus 4 plus or minus the square root of 5. The final thing we need to find is the turning point. And as we're in turning point form, we know that if we have negative x plus 4 all squared plus 5, the turning point is simply when x plus 4 equals 0, or the 0 of that bracket. So we get that x is equal to minus 4, and the y value of the turning point is this plus 5 out at the end. So we have minus 4, 5 as the turning point. So we now have the y-intercept of the graph, which is at minus 11. And we have the x-intercepts, which are at minus 4 plus or minus the square root of 5. And we also have the turning point of this parabola. So that means that we can now move on to sketching the graph. So for this example, I'm going to start by plotting just the y-intercept here and the turning point, which is this coordinate here. Because I don't really know what the numbers minus 4 plus the square root of 5 or minus the square root of 5 are. What I do know is that when y is equal to minus 11, that's some point down here. And when x is negative 4 and y is 5, that's probably somewhere about here. So that point there is the turning point. And there's only one way I can draw a parabola, sort of this shape here, if I want it to pass through a y-intercept and a turning point where those points are. So sketching our parabola, it might look something like this, where we can then label that this was 0, negative 11, and that this was the point that was at minus 4, positive 5. And this must then be one of the x-intercepts, and it's the more negative one, so it's going to be minus 4 minus the square root of 5 comma 0. And this is the more positive x-intercept, so that's going to be at minus 4 plus the square root of 5 comma 0. And we now have the full graph sketched. So just before we move on to our next example, I just want to draw your attention to the negative sign that was out the front here that I've just put in orange. So instead of being concave up, or the normal way that a parabola is orientated, it's now what we'd call reflected. So it is now concave down, and that's the shape that we saw that we needed to use to go through the turning point in the y-intercept that we had found. So for part D, we have the graph of y equals 3 over 2 times x minus 2 all squared plus 1. So this equation is given in turning point form. And I'd encourage you to pause the video and have a go before we go over a brief commentary of this graph. So you'd find that x is equal to 0, and that gives y equals 7, so that's the y-intercept. And then the x-intercept, you'd let y equals 0 and attempt to solve for x, but you'd end up with the square root of a negative number down here, which would indicate there's no solutions or no x-intercepts for that graph. You'd then look at the turning point, and we know that in turning point form, we have x minus 2 equals 0 would solve that for the x value of the turning point, so that would give x equals positive 2, which is what we've written out here. And the plus 1 that's just here is the y value of the turning point, so we get 2, 1 as the turning point's coordinate. So using the y-intercept of positive 7 and the turning point of 2, 1, we could construct a graph that wouldn't have any x-intercepts, so we couldn't plot them because we couldn't find any. So the graph would look something like this. And you can see your turning point at 2, 1 and the y-intercept of 0, 7. And from a graphical point of view, you can see that there's no x-intercepts to that graph either. The last thing you could have considered would be the discriminant. So if you expanded out the turning point form that it was given in, you'd find that y equals 3 over 2x squared minus 6x plus 7. And using the discriminant is equal to b squared minus 4ac, you'd find the discriminant's value is minus 6. And because it's negative, that's another way of knowing that there's no solutions to the equation, and that means that there's no x-intercepts of the graph. So for part E, we'll go through this example fully. And for our sixth example, part F, we'll just give you a brief rundown of the process. So for this one, we have to sketch the graph y equals 2x plus 1 times 5 minus 2x. And once again, we're going to start out by finding the y-intercept of the graph, which is when x is equal to 0. So therefore, we would have y is equal to, and we'd have 2 times 0 plus 1 in the first bracket. And then in the second bracket, we'd have 5 minus 2 times 0. And that would give us y equals, and in the first bracket, we have 0 plus 1 is just 1, multiplied by 5 minus 2 lots of 0 is just 0. So we have 1 times 5 overall. So the y-intercept must equal 5. Then we can move on to finding the x-intercepts of the graph, and we do that by letting y equals 0 in our equation and solving for x. So the equation becomes 0 equals, and then in the first bracket we have 2x plus 1, and then that's multiplied by 5 subtract 2x. And in factorised form, it's really easy to apply the null factor law to find those x-intercepts. So therefore we would say that 2x plus 1 could equal 0, or that 5 minus 2x could equal 0. If we subtracted 1 from the first equation to start us off, we'd find that 2x is equal to minus 1, and then dividing both sides by 2, we find that our x-intercept occurs at minus 1/2. The second x-intercept, we could add 2x to both sides of this equation, and that would give us 5 is equal to 2x, and then dividing both sides of that by 2, we find that the other x-intercept is at positive 5 over 2. The final thing we now need to find is the turning point. And in this example, I'm going to make use of the fact that we know that the turning point is halfway between the x-intercepts. So that's kind of like finding the midpoint of the two x-intercepts. So halfway between negative 1/2 and positive 5 on 2 is actually positive 1. And to show where that comes from, we can have x is the average of negative a half plus positive 5 on 2. So that will give us x is equal to a half times, and this is going to be the same as 4 on 2. And then a half times 4 on 2 is the same as 4 on 4. So that gives us 1. Then to find the y value, so if that's the x value, to find the y value of the turning point, we sub 1 back into our equation. So that's going to be 2 times 1 plus 1 in the first bracket, and then 5 minus 2 lots of 1 in the second bracket. So that will give us y is equal to, the first bracket is 3, and the second bracket is also 3. So that gives y equals 9. So the turning point is 1, 9 for this graph. So now we have the y-intercept, which is at 5, an x-intercept at minus a half, and an x-intercept at positive 5 on 2, as well as a turning point at 1, 9. We can use all of that information now to graph this parabola. So negative a half might be this position here for the x-intercept, and 5 on 2 would be about here. And you might like to think roughly about their decimals when you're placing them. So this is about negative 0.5, and this is out at 2.5. And then we know that we have a y-intercept of 5, so that might be somewhere here. And then at 1, we'd have a y value of 9 for the turning point. So now to draw a parabola through those points, our graph would look something like this. And to finish off with, we can just label all of the coordinates that we found. So the turning point was 1, 9. This was at 0, 5 for the y-intercept. This was minus 1 half 0 for the x-intercept. And our last x-intercept and key feature to label was 5 on 2, 0. So that's the final graph for part E. For part F, we'll quickly do another example of graphing from a factorised form. And once again, I'd encourage you to pause the video and have a go at sketching this graph before we give a brief commentary on how to do it. So we'll start off by finding the y-intercept, which occurs when x is 0. So substituting x equals 0 in and solving for y is giving y equals 10. Then the x-intercept of this graph, when it's in factorised form, we use the null factor law. And overall we find that x could equal minus 1 or x could equal positive 5. And then the turning point, again we're going to utilise the fact that it's halfway between the two x-intercepts. So we're essentially finding the midpoint of the x values. So we can do minus 1 plus 5 over 2, which gives 4 over 2 is 2. And then subbing that in, we can get the y value out of negative 18. So now we can use our y-intercept, our two x-intercepts of minus 1 and 5, and the turning point at 2, negative 18 to sketch this graph. So plotting those points and joining them with a parabola shape will give this graph. So after this video, you should be able to determine the coordinates of key features of a quadratic graph, and those key features include the y-intercept, the x-intercept or intercepts if they exist, and the turning point of the parabola. And you should be able to sketch a parabola from the key features you've found from any given form of the quadratic. So that means you could be given general form, which examples A and B covered. You could be in turning point form, which were our second two examples C and D, or it could be given in factorised form, which was our final two examples.